Okay, let's start again. So we now welcome Eduardo Rodriguez, who is a physicist working at the University of Liverpool and at CERN, who will talk about Scikit-HEP, which is an ecosystem for particle physics analysis. And this will last 2 hours. The floor is yours.
Hi, everyone. So, yeah, hi, everyone. Yeah, so we're changing a little bit topics. And first of all, I actually very much would like to thank the organizers, in particular Thomas, for the invitation, for the really kind invitation for us to come in. What is effectively the first time that we join this kind of schools that with something that, yeah, it's domain specific for particle physics. Although, as you will see, I hope that's part of the game here as well. Many of the things that I will show you, in fact, are not domain specifically. And I hope you will find them interesting, useful for your daily life, maybe. So, and the other thing I wanted to say as well concerning these lectures, because the subject is much less known, I would expect, compared to some of the other ones. Certainly the foundational libraries that were discussed very much extensively in the last week. I will have two notebooks. This one is a bit longer, but the second one is really trivial to get to an introduction of what this is about, not just getting a dive straight into the packages, but give you a bit of idea how we got there and so on. I think this makes a bit of sense. So don't worry that the first 15 minutes will not be playing with code, but this is yeah, I think it was a good thing. All right, so I'm not going obviously through the abstract, which you have read, but the first thing I wanted to say that is to connect a little bit particle physics with big data, which explains why we're trying to have this ecosystem that engages with the data science community rather than having our very domain specific frameworks such as root. So this is a different topic. So we try to reach particle physics and big data, and just wanted to mention, by the way, that in particle physics, the root team now advertises this is the root is our big C++ project for data analysis in high-energy physics, and is also the format which we use across the board. And now the advertising that we have over 1 exabyte of data already in the root format, which is completely crazy actually. So we in a way we are already in exascale or area, or at least just getting to that. I wanted to set the scale as well, to tell you a bit what kind of data we're playing with, how much data we are accumulating, and so on. I have a few plots, historical plots. First of all, it's nice to see that just 4 years ago, the CERN data center had accumulated something like 200 petabytes of data. So from its inception, from the very beginning of CERN, so it's in mid 50s. This is already pretty amazing by itself. Now, what I find even more interesting is that in the 1.5 years that came just after 2017, they accumulated 50% more data compared to the last, you see, to the last 60 years almost. Well, roughly, yes, 60 years. So it's very impressive. One of the reasons, of course, is the Large Hadron Collider that started taking data at some point, and that has and that you can see here in this plot. These very small amounts of data before 2010, and then we're starting, and in particular in the last few years, you see the amount of data. This is terabytes. It really is a huge amount of data coming in purple there from the LHC experiments we see. Okay. So, and then I wanted to connect with the big data world by making a comparison with this. Probably you may know this, the Amazon Snow Mobile, which is a truck that allows you to contain there inside 100 petabyte data. And also wanted to look at a throughput of this system, how you can actually get the data in and out of it. So if you look closer into their specs and what they can find online, they support the 1 terabit per second of data transfer across multiple smaller connections, which is absolutely crazy. And then maybe I should have said at the very beginning, but I work on the LHC-B experiment for big flavor physics experiment at the LHC, and we're starting a new big run in 2022, so next year. And for our first stage of the high-level trigger, our fully software trigger, we're going to get a throughput of 1 or 2 terabits per second which is kind of the ballpark as well of this truck. And of course, I'm not. This is joking. I'm not suggesting that we use Amazon trucks for our trigger system. I thought it's quite funny that the numbers match pretty well. So this is our software trigger, by the way, first level, which has to run on GPUs to be so that we don't really damage our physics program, and we can really exploit as much as possible the physics goals that we have for the experiment. Okay, so if you're here, I don't have to tell you why Python is so important. Again, just a few numbers to set the scale. Just on the number actually of data workers worldwide, there's something like 50 million workers worldwide, and the tools that they use are really dominated by Python. And again, I have a plot here where you can see that all the big ones, the big blobs, the main contributors, all have either pure Python packages or have a Python binding, Python way of working. So this tells a bit why we really want to profit from this huge ecosystem of the experience and documentation, everything that comes from that actually, just because it's a whole world out there. So this is obvious. What I wanted now, finally, if you look at Ranji physics, what's the adoption of Python across it? So I have there was this nice survey done by a colleague of mine on the CMS experiment, again, a big LHC collaboration experiment, where he looked at the number of GitHub repositories that were not forked by CMS physicists. And you see in terms of sampling, he could actually get repositories from over 3,000 people. And even on non-fork repositories, he ended up with almost 20,000 repositories across 7 years. So this is enough statistics to see a bit the trend. And the trend is on the right, on the plot there. You can see that in blue that as of 2015-16, we had less and less C++, and Python was just taking over everything. And Jupyter Notebooks, by the way, in green is also Python, right? So you can see that Python is dominating ever more. And you also see the crossover is somewhere in 2019. Funny enough, if you look above at the Google Trends for popularity of packages of programming languages, you also see that 2019 was more or less the year for Python, where it took over Java. These are interesting trends, I find, and also explains a little bit why, well, in some sense, why you're here, actually. So takeaways. Particle physics and data science really deal with big data and share lots of requirements. And there's a big world out there with lots of extensive, powerful, well-maintained and documented software packages, the whole ecosystem. And you saw a lot of it last week, already a little bit this week, despite it being now more domain-specific in the morning. And we really want to profit from that. And that's the reason why Scikit-HEP in particular was created. I just want to have, before I go to Scikit-HEP itself, I just want to make a little interjection here on the big Python in HEP, PyHEP, a big data ecosystem. Again, if you look just 4 years ago, and you may have seen this famous by now plot from Jake van der Plat on the kind of software stack coming from foundational libraries, of course, Python itself, NumPy, Jupyter, Matplotlib, Pandas, scikit-learn, and then domain-specific ones such as AstroPy that was very recently presented. You might ask yourself, where is particle physics in here? And it is true that around the same time when this was created, there was actually no such domain-specific library. So that's also okay. So you may not be too surprised that some of us came up with the idea of achieving that whole. So this is again to show that there's recently a paper about NumPy in Nature, and it was nice to see that usual suspects over there, even Scikit-HEP, in spite of should have been in the domain specific, but it's really great to see that there was a complete maybe not, but at least a pretty comprehensive overview of domain specific NDAs are out there. All right. But before all of these activities also not out in the blue out there, but there's also a community around it. And one of the ways the community talks to each other and exchanges and shares experience is via the HEP Software Foundation. So whether you are an experimenter group or even any individual, there's a very easy informal way of communicating here. And at the end of the notebooks, you will have some links if you want. And we also prepared. So there's various working groups, in particular the PyHEP, the Python HEP working group, which I started some time ago. And we even have in early July a workshop. So if you are interested in Python for physics in particular, you more than I mean, it would be really great to see some of you connecting. It's also an online event, by the way, so there's no constraints apart from maybe from the time zone problems, but these are almost unsolvable. At least it's a three-body problem, so quite difficult. Okay, so in terms of Scikit-HEP community projects, there were several ones. Of course, Root is actually C++ framework, the analysis framework by CERN, and all the other ones were community projects mainly oriented to Python. So Scikit-HEP is what I'm going to talk about, but there's some other ones as ZFit, also Coffee from in particular CMS colleagues working on that. So there's quite a few things that have happened in the last just 3 or so years. So Scikit-HEP, I'm here, but well, first of all, because I co-founded it a few years ago with a few colleagues. It's also the oldest one, and it has to be said that it is also the big project, the bigger of the projects in terms of the number of libraries that it provides. And I should again stress that these are not domain specific, incomplete, but many of them are completely generic. For example, histogramming, and you will see that. All right, so that's what I really wanted to say. Also, a shout out there, because we try to engage, have a community of developers and users. By all means, if you want to engage, you should really feel more than free to do so. Also, I should say that as you've seen, realized by now, these packages are not there since 20 years. So you might, if you are going to play with those, maybe you will find something that is not perfectly matching what you would like to have, or maybe it actually has a bug. So you just could try and contribute, and this is more than welcome. Okay, the links are here, and that's all I wanted to say as a kind of introduction on HEP and big data. At some point, I'll stop after the introduction for maybe some trivial questions before we dive into more specifics. But let me just give a proper introduction to Scikit-HEP. So I mentioned this thing already, the two notebooks I had prepared separately, actually. And the main idea of the project had always been to create an ecosystem for particle physics data analysis in Python, and build it around a proper community of developers and users, because if in the end, really, you want to have both people talking to each other in both directions. And we have to promote high standards, well-documented, easily installable packages. As I'd like to say very often, you can have the most amazing library, but if it's not easily installable or installable actually even in a trivial way, then it becomes almost useless because people move away. You will get annoyed as how difficult it can be to use it. And some keywords that are really important to us, of course, is collaboration, reproducibility, interoperability with the rest of the ecosystems, as I mentioned already, in particular with the data science world, and sustainability. And as you can imagine, this is a challenging one to sustain. It's not just a matter of putting out there a package, but then maintaining it, sustaining it, and evolving it is a fair amount of work. This is something that has to be cherished. All right. So in terms of topics and packages, finally getting to the core of the discussion here. So the main topics, first of all, data manipulation, interoperability, I already mentioned, data aggregation and histogramming, modeling and fitting, statistics, visualization, and here we profit from what is already available. Actually, in many places you will see it, and then also some HEP-specific things to do, for example, with particles and decays, and some other even more HEP-specific libraries. In terms of logos, but this gives you a reasonable overview of what we are providing. You will see, so these are packages to read root files and manipulate them with the non-flat structure, not table-like structures as NumPy, vectors to use to play with momentum vectors for momentum and so on, for momentum and so on. This is all for statistics, particles and decays, histogramming and visualization. You see also there's several of those. So, and this is the kind of, just to whet your appetite, this is the kind of things that we do in our field. So even very fancy histograms, multi-dimensional histograms here, playing with particle information, decays and stuff. I should also mention, by the way, that the project has now, well, since a while now, a year or so, a meta package. So this is the Scikit-HEP name itself, just the name. And in fact, this is the thing that I have used here to install all of these packages. See the Scikit-HEP package versions that I used in this tutorial. This makes it easy because I can provide a consistent set of all these dozen or so, even a bit more than a dozen packages of the ecosystem in one go, in one line in my conda environment file, rather than having to specify all of them and taking care of versions or anything like that. I can just make a release of the meta package and make this. I particularly like it for tutorials. So that's all I wanted to say. And well, actually a little extra thing, which is to thank some of my colleagues for knowingly or unknowingly providing material and inspiration for these tutorials. Sometimes I just stole from my colleague packages and tutorials some of the information that I splashed on these tutorials to give you an introduction to. Okay, so I wanted now to get into the packages themselves with the introduction. Is there by chance any very general question that was posted on Slack? Otherwise, I'll start with the first couple of packages.
No, not yet. So
okay.
You may continue.
All right, thanks. Yeah, I'll bug you a few times, I think, because also speaking to a screen, unfortunately, we can't be live for 2 hours. It will be a bit boring. So I will make a pause every now and then for anything.
Okay.
All right. So first thing I wanted to start with is very kind of quick packages, easy packages, particles and decays. Well, because particles and decays really are central concepts in particle physics for these reasons. So you had to have really a package for each of them. But there are more serious reasons why you would like to have a package, as you will see in a second. So those are the two packages, particle and decay language, that I wanted to introduce you to in these notebooks. So first of all, particle. So you may know this big international group, Particle Data Group, which is the international collaboration since many years, I think in the early 50s, that provides a summary of particle physics information, all kinds of review articles as well, and summary tables, you name it. This is the website, it's linked from here. And one of the things that it does, it produces every year is the review, an update of the review of particle physics that is a big document, almost a Bible, with all kinds of information about particles and decays and some other things as well, including interactions, cross-sections, you name it. And you can see it's huge. For example, the 2020 edition had over 3,000 new measurements, so it gives you the scale of the book, quote unquote, the book. And one of the things that is directly of concern to us here is that it also provides, as part of its information, a set of downloadable files with particle data. So those are computer readable by definition. In fact, if you look at the format, funny enough, because of the old times, this is legacy, they are in a format that is friendly for Fortran, so not quite what you would use nowadays. And you can get here, by the way. But they contain a lot of information. But if you want to make any use of that, you will have to parse it yourself, or copy and paste bits and pieces. That's clearly not what we would like to do. And so that's why he motivated us to try and provide something for everybody that you can then use programmatically, Pythonically as well, and well maintained and so on. It also provides, by the way, some Monte Carlo MC, so simulation identification codes in the package. So that's basically what the package is in short. So PG, the data tables, the information in those downloadable files, but in a way that can be digested and programmatically acquired and so on. And also all the PDG IDs, the identification, the code number that identifies uniquely every particle, and a bunch of converters as well. So let me start first with the PDG ID class. I will not mention too much about the converters because that's becoming too niche. I still have it in the notebooks, by the way, and that's often the case that I put more information there than what I could possibly do live in 2 hours. There's no way. Actually, the last notebook, if you wanted to look at it properly, it will probably take 2 hours actually. But I wanted to give that information because if you do it, if you go through the notebooks afterwards by yourself, you have not just a few pieces of code that you can run in a notebook, but also information, some background information on what it means and why it's there and so on. Right? So this is why I'm sometimes skipping bits text because largely I'm talking about it. But for the rest, I can just skip small sections, and you can, if that's of interest to you, then you can go and check the converters, for example. All right, so I should start now actually running a bit. So I'm going to import this PDG class and checking what it is, for example, for for the number for the PGG ID to 11, which is actually a pion, a positive pion, but it doesn't tell you my information. It just tells, okay, it's PGG ID 2011, fine. If I start putting a random number, at some point you will find a number. It will actually tell you that it's not valid. The reason is because the PGG ID is an integer in the end, but it's a very sophisticated integer because it encodes lots of information such as the charge parity of the particle, the spin, the charge. There's quite a lot of things. In fact, the kind of information that it encodes is what you can get from this info method. So you see that even for the atomic number, because it also includes some information of a few nucleons, the spin, orbital angular momentum, the spin. So this is J is the total spin, the absolute ID, the charge. You name it. You can see that it's quite a long list of the three times the charge of the particle. There's quite a lot of things that you can ask yourself. You can even ask whether it's a lepton, a meson, a pentaquark, a nucleus, a quark, you name it. So all of this information is actually encoded into this integer, and that's why if you start putting random numbers there, you will find something at some point that it doesn't make sense. Of course, for the pion, this is a meson. So whether you take the standalone function or or you acquire the property, it will tell you it's a meson. Okay. I said I would not go into converters because that's a bit too new. So let me go straight into the main class, which is the particle class. Unexpectedly, this is a class to deal with particles, and we just mentioned the pion, the 2011. The 211 PGG ID. So if I wanted to create a particle or acquire the particle, given an ID, this would be the most common way to do that, from just particle from PGG ID. And I get the pion actually. And if you are on your notebook, it then gives you a nice display of the actual particle. So this is indeed the pi plus. Now, admittedly, the most interesting things will be then to do all kinds of search. All the tables are provided by the package, and there's two ways of doing that: find all, which is the default ones, so to speak, and define, which tries to do a single match of what you query, and it will raise an exception if it finds more than one. So depending on what you want to do in your program, this might be a good thing to do. Or if you want to know all of them, then you just call find all. So if I wanted to, for example, to find the JPSI, I happen to know by heart that this is actually the name of it. So you would get it, fine, nothing very sophisticated there. Now, if I wanted to say, I can't remember, I wanted to have this orbitally excited pion, and I wanted to check the negative charge ones, then I would actually just call it like that. I see that I didn't put any of it. Matches all the names that have pi in it, so you can see all of those, and it provides you a bit of extra information, such as the PGG ID, so the coding number, also the mass. Yeah, and you can now if you want to become a bit more fancy, there's plenty of things to do that, and find all can be really very fast. First of all, let me just import a totally trivial and tiny package from Scikit-HEP, which is HEP units GV. So this is, by the way, nothing fancy. If you check GV, it's actually just a number. You might be surprised why we do that. And the reason, compared to AstroPi, why we don't have such a sophisticated system of units is because we don't really change system of units in particle physics. We always run with the same one. And whether it's GV or TeV or MEV, it's just a scanning factor, right? It's not a conversion of a system to another. So that's why you can have numbers. And that, in fact, looking at bugs in an experiment software stack across any years, I can tell you that this is not a source of bugs. So this is actually trivial. It might be as funny as sometimes at the very beginning why we use such a simple thing, but it works pretty well. Certainly, it's very readable. So, for example, in this one line, notice, by the way, that we try to be quite concise. So you should be able to do sophisticated things in one line. So here, I'm actually trying to find a particle that has the bottom flavor. It has no charge, and the mass is between 5.2 and 5.3 GeV. And then because I didn't specify anything else, it actually gives me the B0, and it's the B0 bar. You know, of course, the information is the same, except for the ID that is not the same, the opposite. Again, you can be more, you can be fancier. You can ask very large lifetimes over 1,000 seconds, you name it. And even if you want to say, which are the ones that are stable effectively, you can just pass it lifetime. So you can pass it to find all pretty much anything. So here you would get the infinite ones, so the protons, the photon, the electron. You can even be fancier. So here's lambda function where you would acquire in one line directly which are the pseudoscalar charm mesons. So there you go, they're all there. Okay, so these are all very trivial, such as acquiring the particle. If you are again on a notebook, there's a few representations that are given for you, and if you don't want that, you can of course just take without the representation. And here's the line that you will see very often, or even on the command prompt. That is not a notebook. You will get a bit of information already on what particle you have. And if you want to know everything about, so to speak, a summary of the particle, then you can describe it. And there you see the name, the ID, even the latex there, the mass, the width. Depending actually on the particle, you will get the width or the lifetime. So this is programmatically done on the fly. So you have something that is more significant. So you might have the width for the resonance, and you would have the lifetime for a K-on, for a K-short, for example. Okay, you also have lots of things for your programs and work, even thesis or latex names, CNHL, HTML, whatever, anything you might think of. All kinds of information, as I mentioned in the describe, you can see all the properties, such as also the PDG-ID, and you can acquire anything. So, okay, the only thing still on particles, to make it easy, very often when you are running programs and you want to use them to use information in there, you might want to have something that is readable very quickly. So that's why we also provide a bunch of literals, and we have them for the particles or the PDG-ID class. So you see here, depending on how I import them, I actually get the particle. Oh, sorry, I'll skip to one line. I actually get the particle, or if I import it from the PDG-ID, they actually get the PDG-ID for the file 1020 meson. But at least it's a trivial way to have something in a piece of program that you can share around with people, and they can read immediately what that is. If you are, for example, getting the mass of that, so you go here, just type mass, right, and get the mass. And if I wanted to in GV, then and you go, right. So that's how you play things. Behind the scenes, there are actually a few curated data files that are produced from the PDG data files, but extending lots of extra information that I didn't mention. But there's also extra information that is not provided by the PDG anymore on a regular basis, but we incorporate that, we amalgamate that piece of information, and these are the data files that you are effectively using behind the scenes when you're doing any final search for particles. Just for information, by the way, there are also other things you can do. For example, if you were to produce tables of particles, you could also do it very nicely, profiting from the ecosystem. Here, you would use it as a matter of example because I like it. This very powerful, flexible tabulate library, and you could here make a little type library of all leptons, including even fourth generation leptons. You see that all quiet again in one line there, and the query here uses the same syntax here as the syntax for a find, so we don't have to know two interfaces. It's all the same interface. Right, you can do plenty of things, but we can stay quite a while. I will move on and talk about decays. So if you're especially a fluid physicist, you may know that programs such as ZTTGen that are event generators and that simulate quite precisely the decay chains with all the dynamics and spin and so on. So the way we specify what decay chains we want to generate is via these so-called decay files. We have lots of them, hundreds of them. I also have a gigantic master decay file in LHB, Bell2, and various others. There's 3 where you encode basically what are all the decay chain possible that your program, effectively your simulation is going to take into account. So you also provide a way to parse these big files and make something useful with those. And again, to try to provide it for everybody. And we build on top of the large parcel to do that. So what is a decay file? So as I mentioned, they are gigantic. You will see an example with the LHB one in a second. But I wanted to start with a user decay file. So imagine that I don't want to produce, say generically, everything, the whole universe of decays according to their probabilities. But I want to in this case to generate just a BC going to a BS KK and the pion. So this is what it looks like. So I define my aliases. The particle I actually want to, my BC is my signal. That's what this alias is. And then I have a few things that I want to decay it only to BS pion, and then the BS only to KK. Whereas, for example, generically, the BS has more than 200 ways of decaying, but I want just that one with this decay model encoded and some other parameters for the model. So this is how it looks like. So let's try and play with that. So we have a little class called Decay File Parser, speaks for itself, and let's do it. So as I mentioned, every big experiment has the master one where you really define its universe, your universe of decayed possible decays. So this is ours, and to give you an idea, this is about 500 particle decays are defined with thousands of decay modes. So if you go via all the routes possible, you have I think tens of thousands of them, and it's a big file. It's 11,000 lines. So let's go and parse it. So this is it typically takes 2 seconds to parse the whole thing, and then if you want to check it, you see that there's 500 or just over 500 decays there. You could know lots of things about this, by the way. In particular, even the grammar, the information, and of course a bunch of queries. The grammar is a funny one, actually. I never remember yet. So actually, let me make that into a format that we can actually read. So this is the large parsing decay file that makes the parsing of those decay files. So it's a bit cryptic, and these are all the models that they find and so on. So you can navigate through that at your own leisure if you want. So here I'm just going to read a simple example, which is this guy here of a D star going into 3 possible decay modes, and then for each of those that actually decays, we want to decay. We have the other one. So you see D0 pi and the D0 I wanted to decay to K minus pi plus and so on. Even the pi of 0 has 4 decay modes with their branching fractions. You see most of the time it goes to gamma gamma, but in almost just about 1% of the time it actually goes to something else. So these are kind of Dalitz decays, plus, E minus, gamma, and so on. So off I go. If I haven't parsed anything, I just instantiating the thing. It tells you, hey, you have a decay file. That's it. If I parse it, it does tell you that I have 5 decay modes, decays, defined in what I have parsed. You can also do all that kind of things. Sometimes when you're passing around and want to maybe do a few tests, you might want to copy and paste a bit of a file just to check something. So you can also do that via class method from string. So you don't need to open always the files because they can be very big. So this is all trivial. Now, immediately once you parse, you want to extract information out of it. So the first thing you might want to do is actually what are the mother particles, the ones that are defined, for which there is a decay defined. You have so these are exactly the 5 that were mentioned above here. You see. So D star, D0, D plus, and so on. And let's say that I wanted to print the decay mode for the D star plus. So that's it. So it's actually almost in a different format. Is actually a copy of the file. Not very interesting. It also has plenty of other bits of information that are used by the program that you might want to have. And you can also get charge conjugates. So the BC plus and B minus and so on. Right. So going a bit up to something more useful, you might want to actually build a decay chain out of it. So build all the paths that are possible in a programmatic way. So this is what this build decay chains method is, where you give it one of the methods that you have just checked above, list of decay methods. So also this is one of them. And it gives a big dictionary just because it's a generic way of doing that. So if you were checking something like just the pi 0, you actually have something small because it's just a part of that. Okay, right. And now I'm finally going to view what I have parsed. So this is what this class decay chain viewer is for. Yeah, I forgot. Sorry. Okay. My apologies. So this is what it looks like. So if you were visually, if you wanted to visually see, understand what what are all the decay chains? This is what it is. So it does start with D star. Now he actually has the proper names of the particles with the mask in this case, not just the EVT-gen names. Unfortunately, making things that complicated. The standard names are not the ones used by the EVT-gen, so there's also some machinery to do the conversions on the fly. But you can see that it can be quite complicated. You see the 4 decay modes of the pi 0 and so on. Right. You can also do you can also, by the way, specify to make something a bit smaller. You say, oh, imagine I'm checking on the fly. I'm just switching off the decays of these 3 folks on the way, and that's what you get. Of course, if you were removing that here, you would see that the pi 0 now is decayed, right? Sometime if I go back, it's not there anymore. So you can play with that. And there's also plenty of things for charge conjugation. And here, this is again an area where I left it. Maybe I should have explicitly written as exercises, but you can play with it. There's a few subtleties. The main reason that you don't want to be too clever. So what is not part, what is not available, you don't try to do a best guess, because you might get it correct 3/4 of the time, but then at some point you will get it wrong, and that's always a nightmare to debug. So what's not there, if you made a bug, if you didn't make a link between a particle and its associated antiparticle, it pretends it does not know, even if you in principle know. Now, admittedly, another thing, even if you're not playing with decay files, you might want to do the same kind of play the games with just programmatically with classes. So this is why there's this set of three classes, and the main one being a decay chain that is a collection of decay modes. And decay mode has a final state, and this is what is done by daughter's dict. So I can go through quickly here, but it's essentially you are modeling your final state as a counter, because then you have a few things that are just trivially done. So this is all different ways of saying I have my final state in this one, which is a k plus, a k minus, and a pi 0. But there's various ways of doing that. So now I can move on and create a decay mode. So you see I'm creating my final state, a k plus, k minus. I'm saying it decays to that half of the time. And then I say I have actually my model, which is called an EVT-gen model, tau had new. There's a few parameters that I have to specify, and I can even specify some metadata, say, oh, this is for a toy I'm doing with some data sample from 2019, something like that. So off I go, it's all there. And I can go and describe things. So this is just a different way of, just as a practical describe, you also have describe for the decay chain. It tells you what you have defined. And you can also, again, do all kinds of manipulations. So start with the PGIDs if you wanted to programmatically start with that, and build decay chains, right? And you can check your decay. So you have 3 of them. You see actually you have the main one, and then you say the 0 is this decay mode, the k short is this decay mode, and the pi 0 is this decay mode. They all defined there. And if you want to flatten them, so actually give you the full final state, as if you were doing a reconstruction with data, the final state is in fact 2 photons, a pi plus and a pi 0. And the branching fraction is the product of those, is the visible branching fraction. And again, if you want to visualize this thing, just as before, whether you start with decay files or not, then you can do it just like that. Okay, so this is very maybe not domain is domain specific, but yeah, this is still essential, because anybody is in principle playing with the particles and decays. So now I'm actually going to start a notebook on something that has some bits with that which are domain specific, but some other functionality that is completely generic and where you could profit whether you're a particle physicist or not. Okay, so this is histogramming and visualization. Of course, I put them together because they really are so connected in general. Because histogramming is ubiquitous in particle physics, almost anywhere in science. The obvious reason is because you typically have lots of data, multi-dimensional. At least you might even have tables or panels, data frames, whatever, right? But some kind of data with lots of variables. You want to project those data, and you want to aggregate them to to investigate some distribution, and that how you do that, it's always with a histogram, right? So in Scikit-HEP, we in fact have 4 packages. Some are very recent, such as Histoprint, is really just a few months old. So and this is still very much work in progress. So if you have ideas, requests, we should we'll be very happy to hear what you might be interested in or might want to interest in new functionality, whatever, right? So let me start by Histoprint, which is a small tiny package for pre-print of NumPy and other histograms to the console. So this is something that you can run on the command line. So and it only has two methods actually: test hist and print a histogram. So test hist, we could say, is the simplest ever wrapper to NumPy histogram. Which admittedly, this is something also important to realize. A NumPy histogram is not suitable quite for particle physics because histograms are so used, so we really have to make them a first-class object, unlike maybe some other fields. And that's why you see all these packages that have evolved over time to play with histograms. It's so important. So here's a very easy, kind of almost a NumPy histogram. Just even on the fly, you don't even define. Just give it some data, define the bins and title, and you can just display. So this can be super quick. It doesn't require anything. This can also run on the as I mentioned on the command line. Now, if you have a NumPy histogram, there it is. You can also be here. It's just for information. Several types of printing of these histograms, whether you have color, whether you want it on black and white, in color with some symbols. You see, you can play that with all the functionality there, all the examples. But you see, you can have several ones, even stacked. Right. So we have four of them, sorry, here that are combined. I even have this one, which is you can just copy and paste because it's pure text. As I mentioned, you can go and type on the command line. So they won't. Oh, I see. Right, so you can have all the functionality. See, there's quite a lot of things you can do with that. Right. So in terms of interoperability, also should also mention, and you will see, I'm already going ahead of myself, but whether you are using a boost histogram here, defined here, you can still read it as pretty much a regular bin histogram in one dimension. Whether you have a boost histogram or whether you have an histogram that you were taking from a root file, you can just as easily plot them. So you see that the package interoperates well with the ecosystem, in particular our ecosystem as well. Okay, so essentially, really, so this was the game changer for us in terms of histogramming in Python. Was the bindings to the C++ 14 boost histogram library called boost histogram. So this is funny enough. The C++ library is written by an LHB colleague of mine, Hans Dembinski, and then Harry and himself started the bindings for this. So this is really as a very fast and feature-rich, pretty much the fastest thing on you can have at this moment for playing and creating and manipulating histograms. So the Scikit-HEP is providing the bindings for that and all the functionality with some other goodies to make it more Pythonic. Right. So let me start. There's a few places, as you can see, where I acknowledge people explicitly just because I took so many examples from them. So let me start by importing a boost histogram as BH to make it short. These are all standard imports for Matplotlib and NumPy. So here I'm making a Gaussian normal distribution with a million events, and you see that you can pretty much read quite easily. Creating an histogram with regular binning. There's 40 bins between -2 and 10. So I actually want to fill it finally with some data. Sorry, I put that on the same line, and on the nicely on the notebook you will see, okay, has a billion. By storage, by definition, it's going to use double floating precision, and here you have the binning as well. If I check the sum of those folks, though, you will see that it doesn't come up to a million, and the reason is because you still have events. When you sampled from normal distribution, you have a few events, that come under -2 or above 10. And if you want to see them all, it's just flow equals true. And take that into account, and you get back the proper sum of it. So nothing is lost. All the information is actually stored behind the scenes. So you can also plot them in a standard matplotlib. You've done a lot of this in the first week of this lecture, so I don't think I have to go in any detail through all of those lines, but just to exemplify actually what we have in terms of histograms. And you can also maybe make a one definition helper for the lines where you have give it a histogram here, and you make that plot above with a plot list. I'll come back to some easier ways of doing this, because clearly you wouldn't like to be doing that all the time. You can also interoperate totally well with NumPy histograms, by the way. So you have you can just take NumPy histogram, it's all there. And you can go by in both directions. It works fine. Now, why it really shines as well very nicely, and in fact, why it becomes very fast compared to NumPy, especially when you go to 3 and plus dimensions. It's when you go to extra dimensions. So let me make in this example a 2-dimensional histogram. So here, still regular. I'll come back to this regular and storage in a second, by the way, later in the notebook. So here I'm preparing some 2-dimensional data using a multivariate normal distribution. You see that I'm also using the ecosystem, not duplicating anything like that. So just take it from NumPy. Don't need to reinvent the wheel. You can do all kinds of things, fill the data. So again, you see the sum. There's overflow, so that actually on a notebook you even have that information for yourself in case you were panicking. Again, you can make helper functions if you want to produce plots, and this is no big deal. The multivariate actually has two blobs. Okay, and if you want to go above, then you can continue just as well. Instead, you have 2 dimensions. You want an extra dimension, just add an extra regular axis, and off you go. Right. So the data is there. As you can imagine, there's lots and lots and lots of methods and things you can do with. So one of them that is very helpful is you project onto 2 dimensions in this case, so you have one click there. Okay, so there's something also where there's been some proper work, which is a unified histogram indexing an interface, a universal interface. There's even a small package in Scikit-HEP called UHI for this that really gives it a kind of protocol that all of these packages would have to comply to in order to interoperate in a natural way. So you don't have to go and figure what's the exact syntax. They have the same look and feel for the common things. So okay, this is just for plotting as above with the helper. I don't think there's anything fancy. And if you want to just to zoom zoom into say the middle in this instance, then you can make that with the lock, just as in the same lock that you are used to from NumPy. You can also check the contents of a given bin. You check the location of given a certain value. You get the bins, and then you check the actual content of the bin, which actually is this guy for fun. So you see that it has lots of functionality. So I'll not go into all of it. You can play, and you can probably change it quite nicely. He also has, and this is I mentioned so far, we've always been using the regular axis. One of the things that is great about Boost Histogram, even to start with the C++ library, is that you can get all kinds of axis types. The regular, you can have irregular one, so to speak. So you can define it alone. You can have circle, and which in this case is given with the keyword circle equals true. And you can also have category, string, and so on. I'll come back to that in a reference. I'm just going to show you very neatly. So you see here, it tells you this is a special histogram in the sense that it's circular, because it really goes whether you have whether you give an angle or any multiple of 2 pi of it. It's just basically the same bin. So that's why it is so nice to have it defined just like that. You don't have to worry or to normalize to equate them to anything like that. And again, you can plot it and here. So this is, you might have seen this also from NumPy, from Matplotlib, sorry. Now you can have some more advanced uses with different storages and accumulators. So the storages use the accumulators to accumulate the data as you fill the histograms, and then you have different types of storages. It can be double, it can be ints, it can be weighted entries. So you see that it's really very flexible in terms of this. And here, if you were to define an accumulator that is a mean, you see that if I'm only filling with these three folks, not surprisingly, there's three of them. The value is 4.4. If you calculate it, the variance is indeed 0.01. I tell it all that. And if you're using a storage that is going to give you the mean here, so I'm binning in 2.5, and I give that sample above, and I'm using it just for fun because it's quick. The print so the Histoprint package, you see that at 2.5 you have those folks there, and it's got the bin value is actually the mean, because your storage was the mean, not the bin entries, the number that you're filling, right? So you can see that really you can do just about anything with Boost Histogram. Okay, another package, but this not Boost Histogram really is to, if you want to, I want to manipulate, in all kinds of ways in a very efficient and fast way histograms. That Boost Histogram is your friend, so it can be the engine, so to speak. Whereas if you MPL-HEP is more than a visualization, but for something really domain specific in the sense that, for example, the experiments have styles that they want to use for plotting for their publications. There's a few things that are predefined that we do all the time. You want to have easy ways of doing that, and this is a raison d'être of the MPL-HEP package. So let me just import it there, and let me just run actually this guy here. There's four, so I'm making a subplots, 4 plots with various styles. So this is a default one. You may see that it's not quite. In hydrogen physics, we like to draw histograms by default with like that, just really all edges and stuff. You can have error bars, you can fill it. So this guy is doing the same thing, just you see by changing one little keyword or giving extra information such as the errors. It just does the thing for you. This is the hisplot method in one dimension. Now, if you can also do overlay things. So if you imagine you actually want to plot two distributions and see some differences because you have applied some selection, you want to see how that distribution has evolved. So that's typically the use case for these kind of overlay plots. Again, you say you can do the same thing here with the same syntax, but you give it just a list with 2 plots. You make it easy. One of them is 50% higher than the other one for the sake of argument, but you get the point. And even a bit fancier, you can also stack the thing. So this is just by saying stack equals true. So it's not quite the same thing as above, but the second histogram is put on top of the other one, or the preceding one, and you can multiply this. Again, because we use so often two histograms, you can and very often want to know what's an efficiency in a bin. That's typically a use case for some entries. Maybe you have an easy way to do that as well with MPL-HEP. So that's why this package, in fact, is the first one. Even before what I'm about to show is another package that is really about visualization, easy visualization in notebooks. So again, you can go fancy. When I mention that things interoperate well, you see here I'm converting the Boost histogram just defined into a NumPy histogram, but in fact I don't need to do that. And if I want to make the same, I can just give it the H2, which is the Boost histogram. Whether I convert it or not is irrelevant. It just produces the same plot. No big deal. The other thing that MPL-HEP starts maybe as it was how the package started. In fact, it was as I mentioned for starting for the experiments. Very often we have to have a consistent, coherent way of styling the thing, and the experiments have their own styles, which they differ. So you can specify that quite easily. See, just this is simply expanding on top of matplotlib, and you can even define a list of a set of styles. In this case, is the root style, and you also give you some open source fonts such as Firmath that is compatible with the CMS one in this case, and you can make your plot. There you go. So by definition, without doing many things, there are a few bits of information that is displayed for you, and of course you can change whatever you want, right? So you can change the location there. There you go. And you can play that. There's several ways of doing that. Okay. Now we've been playing with Histbooks, with notebooks all week. So maybe not too surprising. We have this analysis-friendly histogramming package that was built on top of Boost Histogram to make, say, interactive work, inspection, very interactive, maybe iterative work as well, that you typically have to do at the very beginning or in various stages of your analysis in an easy way inside the notebook. So this is what Hist is. So really is building on top of Boost Histogram. It depends. So there's a one-to-one. Can't live without it. So here I'm doing as usual, nothing trivial apart from importing the package or the main class that's called Hist with a capital H. And quite nice is this thing. So I mentioned that one reason here is really to make it a powerful, friendly analysis focusing histogramming tool on top of Boost Histogram. That is, you can see it as the kind of engine, the one that does all the heavy lifting. And remember, if you're playing with multi-dimensional histograms, then it really is the fastest thing on the market there. So this is a very one-line way of defining a regular binned histogram with double floating precision. You fill it with a normal distribution, 10,000 events, or off you go. And this is what I meant by it is meant to be used in notebooks, because it gives you immediately some representation for a histogram. A representation is a visualization, at least a simple one, and it gives also some extra information, such as again the entries inside the bin. You see there's again underflow and overflow, and with the flow allowing for that, you can have the information, all the bin entries. So nothing very surprising. Just as well, you can do that. You see, continuing one line, you can make on the fly one dimension, the second dimension still double floating. You fill it with two normal distributions, and you get that representation. Some basic information again there, and you can continue. You get the point. Of course, for 3, you can't really do holograms. Sorry. So it just tells it 3D, but it still gives you a reminder of what we have defined. It either has some equals 0 because you haven't filled anything there. You just defined it, right? Okay. So here is. I've been saying at the very beginning, at the very top of Boost Histogram, that Boost Histogram has a variety of axes possible. Been playing regular for obvious reasons is the one that you use most often, but you can also have, say, a Boolean, simple Boolean axis defined there, or a variable one, so you can define whatever you want as a list, integer, and also various categories, so either integer categories or string category. In this case, it's true or false, so it could also be used as a Boolean. But you might have some other use cases, male, female, non-binary, for example. You might want to have whatever, right? So all kinds of things. So that's what you can see in these one-liners typically you can do very quickly. On plotting, I already mentioned that you get this straightforward representation is already some kind of plotting, but you can go a bit beyond it. So, and you have the first one is the simple plot method, where you can give it a bunch of keywords that are just standard matplotlib keywords. So you can make it fill histogram and put some flashy coloring there. You can continue things because you can actually, as you see, you get back the matplotlib object. So you could go ahead and transform it as you like. Likewise, you can also do plots in 2D. So by default, it gives you something that is reasonable. Again, you see that you don't have to reinvent the wheel. You're just using syntax that you have seen in the lectures last week. And he also plays naturally with the rest of the ecosystem, in particular MPL-HEP for plotting. So if you instead of doing these things, if you wanted to use MPL-HEP because you're using it for some other style, I don't know, for the Atlas experiment, you could just go and do that as well with a 2D plot. So no need to go back and forth. At the beginning, it might be overwhelming, and I think some of these things will evolve. Some other ones will become redundant. But at this stage, and because as often software packages are developed in parallel, there will be some convergence. But at least it is good to see that for the moment there's not much that is broken, or very little, hopefully. And you can really interchange the various packages and take the best that you find in one and use for the other. So, for example, you could use the heavy lifting with Boost Histogram, and then by the time you're playing in your notebook, you just extract stuff with Hist, and that's it. There's no more. It becomes natural. So I quite like this one here. So let me just plot it and show you. So this is it's a two-dimensional histogram where you would like not only to look at the distribution, but also project on the sides the actual distribution in the one dimension. So again, you can use this for that. You see that here you are using the data, and somewhere there you go. You have a helper. So you could try and do this in plain matplotlib, and this, of course it is possible. Admittedly, it will take quite a few lines of code. Whereas here you have this helper method plot2d full, and the full. The extra underscore full is what it tells you. Oh, I'm going to do a bit more than just a 2D plot. Namely, I'm going to have the projections given to you, so you can have an idea of how things look in each direction specifically. So if you were looking for outliers, it could be resonances in some other 2D plots, for example, then it's a very nice way of doing it. And you see, okay, here admittedly you are passing lots of keywords to change defaults, but you don't really need that, of course. I could just remove it. You can just go on. Not sure what the default color is. Interesting. Okay. If you want to on visual, you can go and change anything. Matplotlib style again. Okay. I mentioned this connects indirectly well. So again, if you wanted to use MPL-HEP, that's the way to do it. You don't need. You can do your projection on a one dimension, and you don't have to make any explicit conversion anywhere. Another thing, this is very important for all kinds of work that people do in high physics, is to make pool distribution. So you want to, for example, you make a fit, and you want to check that your fit is giving you is not biased, and you also giving proper errors that are not underestimated or overestimated. So these are pool plots. So there's a few helper functions to do that for you, just because it happens so often. So here I'm to play with and to reuse uncertainties. I'm actually importing the uncertainties package, and I'm preparing on the fly. A PDF, which is a normal PDF. Making feature again. I want this. I still need to start with something. So let's just generate a normal distribution again. Typically, they are supposedly to be Gaussian-like distributed for a standard pooled study. And then you see the Hist provides a method called plot pool, not just plot, which is for 1D, a typical histogram, but actually the underscore pool for that. Again, there's lots of keywords there from matplotlib to change the feel and style. But what is important to say is that essentially this is one line. You pass it a callable. You can even pass it. You can make stuff, and this is what you get out. So here is your generated data, fine, and you have fitted it. You can also check the pool. So by how far the data points are with respect to the line, the fitted line, you see nothing to worry about. You see everything is within two sigma, two standard deviations from the fitted thing. There's no outliers, so it looks good. You can also make it simple PDF. You can give any other function if you wanted generalize to something that is not Gaussian-like, but just because Gaussians are so used, you can, or normal distributions for some of it, you could say you can also do the same with the keywords. So you get the same stuff with the just not even having to define your PEF there, but just saying it's standard. Please give me a Gaussian distribution, normal distribution. Okay. So I think I will run one more on student set and notebook, and then I'll stop a second to see how people are going, are feeling about this. Okay. Still have 1 hour to go. Okay, very good. So yeah, so I talked about how you manipulate data, visualize it, meaning aggregate those multidimensional data files. Aggregate those, play with them, project. You can slice. You name it. You can stay here forever, seeing all the functionality, of course, in these packages in terms of slicing and projecting and plotting. But it gives you at least, and I think this is a general feeling, by the way, of this tutorial. It really is meant to give an overview of what's going on, because you could spend probably 2 hours in most of these packages. But I don't think this will be useful, especially for a first hello world. Here we are as an organization. I think it was more interesting for you to get a reasonable overview of what we can do, what is there. So the other thing, the data has to come from somewhere. I mentioned at the very beginning that root is our format, but root as a program, as a C++ library, is a very heavy library, many dependencies. So I think the installation itself is over 400 megabytes by now. So it has Python bindings, but you would have to have the whole shebang. Windows is problematic. So that's some of the reasons why the idea came up to have a pure Python I/O library that allows you to manipulate root files without having to have root installed. Kind of funny, right? It's a root file. You can work with it without actually having root, so it doesn't know any. Well, it does know a lot about the root structure, how data is structured in memory and layout in the files, but you don't have to have root installed. So it's very lightweight. It depends on NumPy again, and you can expand that very importantly into non-flat data structures. So complex data structures are a super important particle physics. So jagged arrays if you want, and this is the awkward array package. But let me first start with opening some files and the introduction of root, which is in one line the root I/O in pure Python and NumPy. And because it does that, it really is the bridge between the data science ecosystem around NumPy and SciPy ecosystem and the HEP data. So this is what is written there, and just reminding again how important it is that we don't have only simple types, but we also have complex types and complex structures inside those root file formats. They were invented precisely because we can have very complex structures, data structures, vectors of Lorentz vectors, and entries that depend on an event-by-event basis. Sometimes people come up with all kinds of structures that are even funny how complex they can become. But in any case, it's hardly ever the case that you have a pure flat structure in a root file. So you have to have something that works with that file in an efficient way, in an easy way as well. So this is what awkward array is doing there. But okay, I think it's enough introduction. You can again find a bit more if you want to read at your own leisure afterwards. So I'm going to import uproot. Yeah, no big deal. I have indeed not installed xrootd. So if you want to use not the HTTP, for example, protocol to open root files, but xrootd, which is a very efficient one, this will not be available. It's not necessary for this notebook. I could have. No, I didn't think about that. Actually, I could have installed it as well. It's not available for Windows though, so that's probably why I forgot. But yeah, no big deal. So here there's inside data. There's a few samples. These are the ones that I already used for Decay language, and these are 3 files for the remainder of the tutorials. So this is an example file with a little sample. We see what that is. Okay, so it tells you there's something behind. There's a structure there in a kind of directory like. If I want to check what's there, so I have a tree. So the data structure that we have, the n-tuples that we have in root files in Physics, they are called trees, T-trees. You can get the keys, which are the names of those trees, identify them. Here's event. Let's just ignore. Not really important, but this, you always get the last version anyway of what is available. But if you had several ones, this could be something other than one. Let's not just dive into that. But so in this case, there's only one n-tuple. You can get hold of it, or the tree, and you can again check keys to see what's inside. You can see that this n-tuple has these variables, so you can think of that as columns in a pandas data frame. So you have the event number, the run number, and then you can see there's two particles actually, one named 1 and 2, and you can have the x momentum, the x component of the momentum, the y, the z, the eta, the phi angle, and the same for the second particle, and even have the event mass, the m. So let's check what that is. So this is what we call a branch, not a column as in pandas data frame, but a branch in root language. So you didn't change that, you still have it. In spite of not being root, but it mimics clearly the language, so it is a branch. So you can get an array of that. So it could be an awkward array or a flat, say, standard array, but in any case, you do get via the method array. Actually, it tells you here there's 2,304 entries. These are double float. It already gives a bit of information as you talk. All right, so there's also ways of getting all the arrays in one go. So here it becomes a little bit more complicated. So you stop at the second one. You can see that it tells you something about that. Now imagine you want, because you're used to doing all kinds of manipulations of data in pandas. You want to extract that information into a pandas data frame. You see that instead of getting the array here, which is in fact a local array behind the scenes, you can tell I want to use pandas as a quote-unquote engine. So you do that, and now if you visualize the data frame, you see all the entries that are exactly the ones that I will mention here as the keys, the columns of your tree. So this looks more familiar to many of you. Again, you see, so there's 20 variables and those 2,304 entries. Now you can do the same. Okay, if you want to check just a few of them, so ahead, and you want to specify, you can specify in the list the ones you just the ones you are interested in. For example, the PT could have the mass actually. So off you go. I'll come back to the mass in a second, by the way, because you see that these are not completely random. So all right, so that was it, just to give an idea of the structure of the files. It's admittedly a simple one, but we're going up in complexity for the remainder of this notebook. And for that, I'm going to use another little file sample of mutants. So it does have a collection of events with an irregular number, or event by event, potentially different number of mutants per event stored. So again, the same thing. It's still called events. The T3 inside, so the same game. I can check it, and so there's 100,000 entries in there. By the way, yes. Yes, I swear. Okay, sorry. I was getting wrong. Is here? Sometimes that's no. That's probably not. Okay, forget. Sorry about that. I wanted to show, but I'm getting confused now. So let's move on.
You can show it on F events and then show, I think.
Excuse me?
On F events and then show.
Yeah, that exactly that yeah. I think that we are here. Right? Yeah, so this is, it also gives a nice thanks. It gives a nice table of all the information. So it is before anything, if you want to check, oh, I forgot what's inside the file, so this is a nice way of doing that. Okay, No, of course, now I'm there, but fine. Okay, so this is still fine. It's still a square structure as you used to it, for example, in pandas, because it's a number of mutants. So you have the variable actually tells you the number of mutants per event, and you actually see here already that the first event has 2 mutants, the third one only has 1, the fourth has 4, and so on. But this will become very evident if you look at something like a PT of the mutants, where there clearly, if you have 2, you have to look at the PT of the 2 mutants. And the representation tells you that information, because now instead of saying I have 100,000 entries of int type to float, there's a variable number of them inside. So this is what the var is telling you in the representation there. Right? And you also see that, by the way, in the fact that in the first one you do have a list of 2 entries there. The last one you have 3, and those are the 3. So you have an idea. If you want to be even more explicit, you can just plot a few of those folks, on a polyline basis. See 2, 2, 1, 3 entries, and so on. 4, 4, etc. So this is what we call bijagged because it's not a regular. It's not a flat a table. The number of entries, mutants in this case, changes on event by event basis. But the good thing is you can programmatically play with those things in NumPy way, as if you were playing with a flat structure. Oh, sorry, with a square structure, although it's not at all the case. And this is the reason why orchid array was invented. And I have to say that these two folks really were the game changers, because it allowed it to all of a sudden to be playing with the SciPy ecosystem in a proper way, whereas this was not naturally, at least, done possible prior to these packages. So again, I already mentioned the reason for these folks, and you've seen this example in variable size data. You can get mixed types, you name it. So again, we are just a reminder of those folks, and we're going to look at and the exercise here will be to try and look at events with 2 muons, and moreover that they have opposite charts. So you see we're getting, because a very interesting, well-known decay mode is JPSI to mu. This is used for calibration for all kinds of things. PID calibrations in particular, even for alignment. So really, this is a golden mode. But there's more in that event distribution, as you will discover in a second. So let me import again awkward. So typically we do it a short way as NumPy and so on. So import awkward as AK. Reminder of those variables. Remember, so you had mu1, the mu1 PT, and a bunch of other folks that we have seen before. I already went ahead of myself, but mentioning that that var means that the field is jagged, so we have a variable number per entry. We could have a look of those folks. Let's check the first 3 events. So it has 2 muons in there, 2 and 1. The PT, you have the variables, only 1 entry, of course. So, and you even have the mass. Right. So okay, maybe not so bizarre. This is just the mass of the muon, not in very mass of the dimuon system, but just the mass of the muon, which is typically roughly 106 MEGs. So okay, you can get just to say that you can do all the indexing and slicing that you would expect in an NumPy way. That's what I mentioned. It's natural. You can play it. You don't have to go and learn a different fitting library to be able to manipulate all this data. Okay, so standard way of making a plot with matplotlib, so you can have a look at events. Indeed, now you finally visualize a proper way, nothing like a plot that the number of muons per event is varying quite a lot. Okay, immediately there's most of the time 2 or 3 ones, but still. If you were doing that with hist, you would just do it in a line. So you can do, I want regular bin from 0 to 10, and name it like that. Give you some label. It's all double floats, and I fill it with my branch straight away. So you see, it's there's no convention to NumPy, whatever. And this just it works naturally, and you can get the same plot. Not quite, because it's a histogram, and remember, for the notebooks, it gives you this nice representation with the visualization at the same time. Now, I can also become fancy at the mask. I'll come back to masks later, but I can say I actually want to. I only plotted up to 10, but is there a lot? Are there many events with say more than 10 muons in the event? And actually, there's 110 of them. I was quite surprised, to be honest, even when looking at this file. But admittedly, nothing beyond 50 muons per event, which is reassuring because otherwise it would be kind of funny data. You see, so yeah, you can do you can count this. There's plenty. Again, the library contains a lot of methods. You can do type, you can do sum, you can number, you name it. Here I'm checking what's the length of that branch and then making the sum in two different ways. And it's telling me so the length is those 100,000. So I have 100,000 events, nothing worrying. But in total, I actually have 235,000 and blah 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 muons, a little bit more. Right, so you can get all the information for making the sum. Either make the sum straight away with the awkward dot sum, or you make use a standard library sum on the function that calculates the number per branch per event. So there's all kinds of ways of getting into the same result. So you can use what you more used to. You can also specify it, by the way, by a property of the branch, so speaking, rather than having to go by the element in string. You can also check another help function, as many of them, is the type, which is what is used, by the way, in the representation. See that you remember this is 100,000 entries, a variable length, a float, and a float. Now, again, let me plot things, and because I'm looking at the PT, I will probably want to look at these things in logarithmic. Otherwise, you really have something that is so exponentially that doesn't tell you as much as you would like to. Okay, so you have this distribution. There's some structure there with 2 peaks at the low end. Nothing very worrying. I think often this comes from different streams in your data taking, in your trigger that even has some threshold cut or something like that. So don't be surprised or worried by this structure. This is just the way the data was produced, stored. I can flatten that as well for the eta distribution to PT eta. Two variables that are very important when you're working with jets, maybe not with muons, but just for the sake of argument, see that so the data was taken between more or less 2.5 in absolute value in eta. Okay, I'll skip that about timing, but now I'm starting. I actually remember I wanted to look at dimuons as the opposite charge. So first of all, it can make a mask. So this is the usual way in the ecosystem to do. So you end up with an array that tells you just if it's true or false that you have only one muon. So remember the first two events had 2 muons. So this is immediately false, and the third one had 1. So this is true. Nothing worrying. So this is correct from memory. So now I can put that into just a name, a variable for a mask, and I can tell. Let's check how many. So there are 13,000 single muon events, 13,147. So if you want to be maniac, you can also check by some other ways. So here I'm again flattening that distribution, but now as above, I'm saying I want to look at that distribution only with for single muon events. So that's why I'm passing this mask. And there you go. So this is not quite the same as above. In particular, see here there's 10 to 4, and now I'm at 10 to 3. So clearly there was so only a subsample of the events have only 1 muon. Nothing. Well, probably not the ones you are interested in anyway. So we move forward. You can also apply all kinds of masks, which effectively is how you're going to apply cuts in a different way. Whereas if you were using the root ecosystem, you do it in a slightly different way, at least in the past. So you can also apply a mask for muon eta less than 2. So quite you can flat check how many entries there is. Okay, you can do all kinds of. I mentioned already num sum and sum, so you can check how many of those you have. And let's try and make a visualization of this thing. So now I'm becoming a bit fancier. I'm looking at the data distribution with or without the mask just defined. Nothing else is different. So I get the distribution above, no selection, and then if I apply, okay, nothing fancy. This one is not sculpting this distribution; it's just cutting away the tails there. Fine. So and if I apply those masks, right, so true and falses for the whole data sample. So unsurprisingly, it has a mask for every single entry, hence the 10 to 5. So now if I want to plot, check if there's some bias of how things change, whether they are inside or outside that ether mask. I can look at all the PT of all the muons with or without the mask, right? So in one muon events with inside or outside that. So that's what these two masks here are doing. This is the opposite, right? And you see that indeed the distribution in PT is not the same whether you are less than two essentially in the central area or outside, in a very forward region. So either going to very big numbers, you really are very close to the beam pipe, so to speak. So not surprisingly, if you're there, the PT is much smaller. You see, there's very big, there's very small values of PT. So at least visually, I would say, yeah, that does not look bizarre, which is reassuring. It's always good to cross-check and build it in memory. Okay, so now finally getting to what I wanted to play, which is events with 2 muons. So let me first define as before the events with 2 muons. Again, okay, how many? There's almost 50K of them. So okay, enough statistics. I can again look at the samples. This is always the same. Here I have to say this is an old way of doing this thing, because I want to now calculate on the fly the invariant mass distribution of the two dimuon system. And this is the old way with a helper package called output methods, 3 methods. Whereas when now there's a very new package in Scikit-HEP which is called vector that will play with all kinds of vector three-dimensional, four-dimensional in a very nice way. Admittedly, it was really lack of time that I didn't have the time to rewrite the whole thing with that, but it should be more natural. So bear with me with apologies for a few lines where this is not done in a so cool way, but in the end you get the distribution. You can still calculate, of course, your invariant mass, which is the main point after all. So allow me to go through that. You have your number there. Nothing bizarre. I can also check the distance in a cone between the 2 muons. So this is a function, a method in distance in R, which is the square root of the delta of the difference in phi and theta. So it really gives you a cone. So you get the array there, and if you plot that, actually you see that very often the 2 muons are either almost collinear, very close to each other, or back to back, free, right, at a distance of 180 degrees. So this is also nice to, if you want to make some other kinds of studies of quantum chromodynamics, for example, where clearly you would like to look at jet structure or some configuration in your event where you'd like specifically back to back or very collinear events for that reason, right? So this you then apply a cut here somewhere, for example. Okay, so now I'm programmatically, by the time you have your 4 vectors there, here, sorry, so your 4 momentum vectors, Lorentz vectors, you can sum them up. You can say I'm going to create a mask that for the first one and the second one, there's only 2 of them, right? Okay, right? So if you want that clip doesn't exist, you have already selected that. So I'm applying the mask and I'm making the sum, which is I'm summing the 4 momentum. So I have the 4 momentum addition of the 2 muons of opposite charge. So really is now all the mu plus mu minus pairs. I have a vector, fine, which is again an Enoch array vector behind the scenes, and then I can go on and plot it. This is standard stuff. Here, this information for beautifying. The only slight different thing is because I'm looking at very large scales, as you will see in a second, across many GVs, MEVs. Well, yeah, across the various orders of magnitude. You want to look at that in a log scale. I'm using the particle and HEP units packages that I mentioned earlier get some units and particle names, as you see here. So this is just to help myself. Nothing, you see, it's not 50 lines of code, but just a few lines to get that information. And even this very boring, not a clever way of doing it is because otherwise these folks are almost at the same mass. They end up being together, so you wouldn't see them. I'm just doing that to shift it a little bit in the plot. Nothing fancy. The whole thing is just there for the legend. And then you get the plot of those dimuons. So this is distribution in dimuon mass, and the above was to put some labels to guide the eye. So this is the Z0, so kind of 90 GeV roughly. The J psi, which is a 3 point something, and then the phi meson and the rho and the omega that even the eta is very difficult to find. But if you're doing some more clever selection, you will start seeing a little peak for this eta. It's quite cute to see all these distributions because I haven't done any machine learning selection in there. So this is not cleaned up data that you'd use in the proper analysis, and you still spend data across over 2 orders of magnitude there. Quite a cool thing. So these are the links, by the way. I only have two notebooks to go through. Half an hour, admittedly, the last one is a long one. Are there any general questions on all of these packages that were posted maybe before I go to this guy, which is on fitting, completely different. I talked a lot about data itself, how to manipulate the data. So maybe a pointer, if there's anything generic, I'm happy to answer.
Yes, there is one very general question is, can Scikit-HEP be used for general statistics, signal processing, etc. in other fields?
Depends on what you call by signal processing. So some of the things that we also seen this week for time series, for example, which is something that we don't use, then you would not find any kind of software for that. But generic manipulation of data, whether is flat or square or not, this you can use with particularly with histogramming and the awkward arrays. In fact, I have to say, not in astronomy specific, but even in biology, I know that Jim Pivarsky, the author, was in touch with some people because they realized that this could be quite useful for their data. Because it really extends the NumBind paradigm. It's great for when you want to pipe into a machine learning ecosystem because it doesn't digest awkward jagged arrays, jagged structures. But then on the other hand, this package here is providing you all you need to be able to exploit those data in an efficient and natural way. So depends. I would say that for some cases, yes. For some other ones, such as time series, come to my mind that it's not something we do, so we wouldn't have much.
Yes, thanks. And I see also that in the chat, Carl made a comparison between the histogram and the NumPy histogram and got a 10 times improvement in speed. So yeah, surely it can be used for histogram in different fields.
Yeah. I can say it non-biasedly because I'm not the one who wrote that package, but it really is super fast compared to NumPy. If you use NumPy histograms, you use them, you will see you'll notice the difference. Yeah, it's pretty cool. Also, as you saw, I hope I gave a flavor of that. I find the API was also quite natural, and very often, as you saw, we really try to mimic everything from the scientific ecosystem. So it plays in well. You don't have to learn a completely different API, which sometimes was the case with the old Physics software. Okay, so if there's nothing generic, then I'll continue with fitting and modeling. All right. Okay. Thanks for the questions. I see we have half an hour, so we should. I think we're on time in the end. I'm quite happy that we have enough time to go through all these topics, which is quite a lot. You probably have your head like a pumpkin nowadays after those 5 days of lectures, but hopefully at least you got interested in many things. So this notebook is indeed about fitting and model building in general, because fitting is as a generic word. You can fit lots of things and you want to get parameters out of it, but the typical use case, well, you want to model your data, extract some variables, maybe some some nuisance parameters are also involved, so things can become complicated, have potentially multiple dimensions you want to fit at the same time. So let me start simple with iMinute, or simple. It's not a simple package, but start simple in terms of before I go to complex model building. So iMinute is the Python wrapper to the C++ Minute2 library that exists since the 70s, I think. There's a library from CERN written in C++. So this is effectively the library that everybody uses in their life, starting as a PhD student. And anytime you have to do any kind of fitting, you're going to use the Minute. And iMinute is the binding 11 bindings for the library, with a bunch of, again, same philosophy, so making it Pythonic and getting efficient bindings that can also be distributed in wheels for pretty much any platform on the market. Even in spite of being bindings, you have the wheels, so you don't have to do from source. 99.9% of the cases I would expect, at least. So it's very powerful. As I said, this guy really is a big engine in hydrophysics. It does amazing things, and these are the bindings to the package. So importing. So the object is Minute. The capital M is a class, and this is lazily the example on the README of the package that does. It tells, okay, I'm going to minimize with a least square minimization. I have this little function in 3 dimensions. You can read it, it's very easy. You can immediately realize what it's going to converge to. That's the whole point of a README example. But what is nice is that after the minimization with migrad, which is a kind of standard minimization method, probably the one more used, you get a bunch of information. So it tells you this is a function call, the number of function calls that were done. So 36 is an example. The precision, so that was used for conversion, and then it tells, okay, my values x and y, z, the values 2, 3, 4, indeed 2, 3, 4, right? There's some errors, nothing very fancy here because the function is so simple. It also gives the covariance matrix. So this really is the big thing compared to what I think was Alex saying when he was talking about AstroPy, is that in the machine learning world, you get plenty of minimizers, also SciPy, but you don't get the errors in the covariance matrix that come with it. And for hydrophysics, that's a no-go. There's no way we can make any measurement without giving it an error. And if it's one variable, you will have a covariance matrix as well. So this is why Minute and iMinute is behind the scenes everywhere. Admittedly, that is really nice to see. iMinute is used by quite a few packages in astronomy and astroparticle communities. So this is something on which the author is super keen, and also explains, I would say, why certain things were developed in iMinute, because we were not just satisfying the needs of a domain-specific folks, hydrophysicists, but there's more people around that come up with requests and so on. So this is one of the places where you see cross-exchange between different communities, and this is so nice to see. Okay, so if you want to be more precise about your errors, sometimes you even want asymmetric errors, which require a bit more of a sophisticated minimization with a calculation of the second order derivatives. Then you can also have Hess, and there's a bunch of other methods that exist also for Minute. So you see, there's quite a lot of methods that you can do. You see, you could spend quite a while looking at all of that. Admittedly, I have to say that thumbs up to the author. There's several, I think over half a dozen tutorials, notebooks on the package iMinute. You can really go from a hello world, so to speak, to very sophisticated notebooks on where you look at performance, you look at the cost functions, all kinds of cost functions, whether you're doing a bin fit or an unbin fit or an extended fit. So there's quite a lot that you can learn there. And again, this is more like an appetizer. So let me take the last root file with a sample. In this case, it's a sample of tracks. This is a toy package. Okay, this is usual thing as before. No problem. So let me check the again. Yeah, here I didn't get it wrong. Wait, what's inside this sample? So it's track length. So this is the number of tracks, the MC. So here you are kind of making a toy. Okay, you have MC, which is the true generated tracks, and the ones that are reconstructed effectively is by a detector. But here is just a toy, and then you have momentum distributions and the MC counterpart. I need to have the PID, which is so if you were to look at that, you see. Oh, also okay. Silly. That won't work, right? Okay. So you could then look at all of those distributions. So you see 211 is a pine. This guy is a kaon. This guy is an antiproton. So you have quite a few particles inside that sample. So this is what I've just mentioned in words for what the legend is. Okay, so again, let's take an array of your tracks, the number of tracks that you have. The same for the simulation, for the generator level, and say you want to specifically look at the X component of the momentum, and you want to pass that on from Mocha array as using pandas. So and then so that's the guy is there actually. So you see, you have the sub-entries because indeed there are a bunch of tracks per event, so that's why you have the sub-entry. But it's all there. You have the nicely formatted by pandas. Okay, how many tracks you want to be more specifically? Say imagine the number of events with 0 tracks, so you check track length equals 0 there, and you make the sum of it with NumPy. No need to do anything special. You have 63 of them. If you want to plot, you have an idea. So that's distribution. Very often you have 3, 4, 5 tracks per event. Okay, this is what we generated. So then there's nothing more than what you decide to generate there. No physics behind it in this example. We use it for the purpose of fitting. Oh, I had written that before as well. Fine. Okay, sorry. That's a copy. That's interesting. No. Okay, this is the momentum. Right. So this is a variable I want to distribute. You see that already by eye, it looks like a normal distribution, so more or less, right, centered about 0. This is what was done. If you wanted to look at some other distributions, you can also that would look quite differently. Okay, to me, the beginning is not ideal because we're not doing anything fancy here, but of course the momentum is you see many things are more like a 2GeV or something, but that's not what we want. Let me go back to that. Okay. So this is the distribution that we're going to fit. So admittedly a very simple one, but it exemplifies how you can play with 9 minutes. If you want going through your at your own leisure, you have lots of information there on statistics and fit it in general, right? If you are an expert, you don't need to learn how to make your likelihood and so on, so you can skip that all anyway. But yeah, otherwise, it's more educative. Again, if you want to visualize with Boost Histogram, you can just as well pass your array. There's nothing more. So here you fill the histogram with that, as you've seen before, and then you can also plot it with error bars. Notice that for fun, I'm not using anything but matplotlib here, and also using. Now, okay, so we're now going to try and fit this thing with the Gaussian distribution, normal distribution, and some and the normal, and yeah, and we also going to need the Poisson distribution for the statistics and analysis. So let's import that from SciPy. We are in the ecosystem. There's no root equivalent in there taken from the Python bindings. Really is inside that properly the ecosystem. This is the score function. Not going into the details, but you see the commutative distribution there. Probability distribution function, you take the, so this is what we're going to be using to check the significance of things. So there's a bit of vectorization to make it faster. So here you see the want to be too fast. Yeah, so the score function with the muons, the mu variable and the sigma variables, just plotting. The interesting bit now is on the plotting and minimization. So again, you instantiate IMinWidth with your loss function, and you initialize with the variables of min 0 and variance of 1, sigma 1. You can take the least squares method and the traditional method migrad, as you saw before. You extract the values and you make a plot of that before anything. Let me just do that. So you have minimized with IMinWidth. Admittedly, is far simpler, is far more complicated than this little function here, right? And you also have plenty of data. So, sorry. Okay. So unsurprisingly, the mu fitted to the shape that was indeed generated as a normal distribution is centered around 0 with a very small error, and the resolution is of 0.5, and it fits very well. Now you can also look at the pools. Remember when you saw the hist package that you could make a plot of that in a kind of a one-liner. So on purpose, I'm not doing that here, and in this example provided, so things are a bit more complicated. There's quite a bit more text. He also tells you why these packages were developed, why they exist. Because if you end up doing these things all the time, you don't want to be copy and pasting or even writing this thing from scratch in your head every single time. So you want to have a one-liner for obvious and frequent things. So that's what that pool is. Admittedly, it's not insane plot, but you see that everything looks reasonable. You don't have more than a variation of in time 1, 2, 3 sigma. Okay, but these are all very simple examples. So you can imagine when you're looking really doing proper analysis in high-energy physics, we have very sophisticated things. So it's not just about fitting a distribution. First of all, you might have several ones. You might have some other reference distribution as well from which you extract parameters that you want to share. So you might have simultaneous fits with where you would want not just the modeled parameters with some nuisance parameters, but also the yields, so the area under those distributions. So the extended maximum likelihood fits. You could have it binned or unbinned, depending whether you have thousands of events or going to the billions of events. It doesn't make any sense anymore to have an unbinned fit. It would also be a nightmare to try and run it. So you would do a binned maximum likelihood fit. So there's quite a few things. And the models themselves can have different components because you might have your signal, and then you have some combinatorics, background behind the scenes, and then you might have two other partially reconstructed decays and some other kind of backgrounds with K misidentified loop ion. Things that can be quite complicated. So clearly, you wouldn't like to explode this thing where you would at some point it would become completely unmanageable. For the sake of argument, let me get back to this way again. Have an easy distribution, but here you see I'm already doing some model building because you're taking a uniform distribution, which could be your background. If it's a very simple one, it would be flat. And then a Gaussian peak, so that would be your signal, your decay mode, your resonance. And then we're going to use an unbin. We're going to do an unbin maximum likelihood fit to the data with the model, and the data is there. So you see again, you have generated a uniform distribution and normal distribution. So that's the signal. Again, you instantiate minute with that Fox function, the PDF, and you give it some starting values. You also give some limits that could be interesting, important in some cases. If everything is very well behaved, you will not need it, but in general, you might give it some limits to the variables. Migrad, as usual, again, and then here you have some less trivial variables that you got out, unlike that little function, trivial function from the beginning of the notebook. Here you have some variables that have something a bit more complicated. In the errors, you have the errors, and you have also the covariance matrix there. If you want to plot that thing, then you see indeed that so in blue, by the way, this is your central value, the starting value. So you were guessing something that is wider than the actual distribution, and you see that as your 20 entries per event per bin there, you have your flat background on top with a signal on top of it. Fine, but as I said, if you scale this to various dimensions, many more variables, many more distributions, this coding becomes completely crazy. It might become very, very difficult. So that's why you have other packages that when you scale up in complexity. Just to give an idea, which is not a toy world. In fact, this one comes from one of the analysis, the expression from one of the analysis of the pentaquark, in LHCb. You see how things can be complicated, because there you have the sum of squares of distributions where you have coefficients there that depends on the angle, and you have three sums over spins essentially, and you have sums of them for various contributions from various, as I mentioned, decay modes, and you have also spin-like complex couplings in behind. You'll even have some other dynamic terms that are imaginary. Try and imagine just writing even this thing in that code above. It would be completely crazy, right? So you need something else on top of Minimit. So the root framework, C++ framework, has rootfit, and the ecosystem now. There was a colleague. So this is not Scikit-HEP, by the way. I really wanted to show the ecosystem. We're not the only ones doing these cool things in the data science world. There's a few colleagues from Zurich. That's why they're here. That wrote this ZFit package that is about fitting with TensorFlow behind the scenes. So that's the final notebook. I realized I was a bit slower in the fitting. And this notebook, by the way, if you wanted to go through all of it properly, it has so much information, it would probably take 2 hours. So that's not the point. But here I wanted to show that this really is a fitting package about model fitting. So complex things, but you can still, if you wanted to write 3 PDFs, it really has A plus B plus C. And if you have D plus E plus F from another fit that you want to do simultaneous, you can still do the sum in writing almost as in a piece of paper, whether you write it as a model in a piece of paper or in the code. So that really is behind the scenes. And as an engine, it uses iMinit for the minimization, not surprising, and TensorFlow for computation, right? It also has phase space, which is TensorFlow based toy generation. So really wanted to acknowledge again Jonas because we started this thing actually quite some time ago to try and get a nice tutorial, and it really helped a lot in getting the bulk of this thing. Really good. So this is I'm taking here a bunch of packages. You see that from ecosystem, the particle TensorFlow, okay, phase space for generating a particle chain. So this is a toy. So nothing but importing that thing. Okay, so this is the latest version of ZFit. Now I'm taking from the particle package a few masses of the B0, the J psi, the K star, the pi, and the K, and so on. And I'm fitting two things actually: a normalization channel from which I extract the information that I can use to then fit a very rare decay mode where I'm expecting a very small signal. See that my very small signal is 120 events on top of 5,000, whereas for the normalization, the reference model, you see I have a very big peak, even more than the number of background events across the whole range. So I'm having a little function here. So I'm not using vector, for example. So I'm doing it the harder way. You're still calculating the event mass on the fly. There's a bunch of things. This is a helper function to smear the momentum, because otherwise you will have a kind of delta function for the event mass. If you're not smearing everything, it would be all MC truth, simulation truth. And then here I'm actually being even more sophisticated for the K star. You are simulating a line shape. You could do without it, but so this is a bit more complicated, but showing how fancy you can be in the toy generation of resonances. So here you see you can read I'm making a particle K star that decays into a K plus and a pi minus, and the B0 is actually decaying to the K star with a mu plus and a mu minus. If you have followed the hints of new physics coming from the LHB experiment, so this is the kind of decay modes that are being used for those studies. So that's all why it's kind of cool to use such examples. So this is the one-liner to generate the number of events with some weights. You are smearing the particles and storing the momentum of the various particles in there. Okay, so let's be checking, just be sure that all the samples were properly generated. All the sizes from the different variables are the same, so fine. Let's finally just visualize what we have generated. So so every event is generated with some weight, some probability according to the position in the phase space. So that's why you have this thing. So you would use it with weights typically, but you see that this is the invariant mass of the B0 typically, right here, the B0 mass. So not surprisingly, very rare. It's a rare mode that we are generating, and that's why you have a small number of entries. And the Q square, which is the invariant mass of the muon, the dimuon system, this is what it looks like in what we have generated. So not a completely trivial distribution. So we want to now you start seeing how you can do the model building. So I'm defining my observable, which is the B mass, that invariant mass distribution for the background and for the signal and the normalization channels. I'm doing also an exponential distribution for the combinatorial background, not just a flat one, but something that has a little bit more of a shape. So this is the parameter of that, the slope of that exponential. You see that the exponential is there. You have to take it from that fit. Oh, that's fine. Wait a second. Did I not? Oh, that's done. Ah, damn it! I did this one. Sorry. Okay, I did something stupid. Let me just restart. That fit is very picky. If you do twice the same variable, it will complain for good reasons. And I think I did something stupid. I apologize for that. We are almost at the end, but I just wanted to show the model building part. Okay. I don't know what I wrote bizarrely because I checked this all before the lecture, so I hope I didn't do anything silly this time. It's doing the sampling, so not surprising that it takes a little bit of time. Hello. Okay, so this is the minimization now. So you see, it was instantiated here. You see, in spite of being Z-fit with TensorFlow, you still can use behind the scenes minwidth, and in fact, we can also use some other SciPy minimizers. So you see that it's interconnecting well with the ecosystem. So you get the fit, so it has converged fine, and nothing really fancy. It's just calculating the slope of what you have generated. If you go above, you check that it coincides with the value that we have given. Now, more importantly, if you put all the data, so this is the exponential background, this is the signal peak. Indeed, there's a kind of a shy peak in there. So we want to do something more because you might actually be biased if you try to fit just like that naively. You might be, for example, you might get fluctuations around that signal peak, and that's why you use a normalization channel from which you can extract the resolution with via simultaneous fit. So here you putting everything to float. So again, you can visualize that. Hopefully that will take a bit of time. Yeah, I should have spent 15-20 minutes for this notebook. Sorry, it's already the end of the lecture. That's annoying. Okay. So now I'm doing the same for the resonant mode, where instead of having a k star mu, we actually have k star j psi going to mu, and this is a decay mode that has a much larger probability, and then hence you can use that as I mentioned, as a normalization channel. So this is a mimicking exactly the same as before, but just with more statistics. Okay, nothing. Let me go quickly through that because there is nothing fancy here. You generate the data, you put them all together, you visualize it. It's going a bit slow. I wanted to show you at the bottom what I meant by the simultaneous fit. And what I was hoping that you could also see is that the definition of these models is very simple. See, because you define your parameters. Okay, you define your parameters. Okay, fine. Finally, you define your parameters in the models, but it's simple. It's just one. It's a one-liner, and the model can be a sum of the two. Right. So this is your signal here, your rare guy, and this is the after the ref fitting. You see that you can extract the signal from there. Fine. So this is the table, the usual table for min width. If you now generate with the resonance with the J psi, so this is a 3.1-ish for the J psi mass, you have much more statistics. You can play the same as before. You have your data. There you go. So that's what I said, right? Here the signal is very prominent, from which you can really get a good determination of the resolution, which you can fit into that guy above. Because here, if you look carefully at the numbers, you will see that I'm overestimating the resolution, when in fact it's not the same. So I can continue, and then I can do a simultaneous fit, which is now I had my two models, and I'm going to put them together. And the way we do this together, there you go, is simply by saying I had my loss functions. So my likelihoods for the two spectra, and I make my simultaneous loss function just by simply adding the two of them naturally. Okay, now nothing more. It's simultaneous fit. Now instead of having the two separate folks, I'm going to say, oh, I actually remember one of the variables is going to be the same. I make the sum, make an extended unbeing likelihood. I minimize the sum of the two cost functions. And there's nothing more to it. It will take a bit of time, and then it's actually doing simultaneous fit. I think Binder is a bit slower than what you would get locally. Okay, so there you go. You see sigma. There's only one sigma, not two of them. And this sigma is completely determined from the fit to the normalization channel, which is then taken as a fixed shape into the ray decay where you can be unbiased. Now, if you plot that together, okay, and this is just for fun. If you take another package, statistics, but this I didn't have the time at all in the 2 hours away. You can also look at the significance of that peak, which is the guy here, right? The significance of this peak, and if you're doing that statistical analysis, it's doing it twice. So maybe I should have done something else here. Okay, so this is the fit. See, now the distribution is different from what you had above, because now it's a proper resolution taken from the second distribution where you have a very significant peak. And if I'm still doing the job, okay, fine. You would see that the significance of that small peak is actually 5. So enough probability that you would claim a discovery of that single mode. But I think it would take. It's doing a try to do a proper calculation of the significance, but I should have put something else. You see that very clear J psi fitted there. Okay, I should stop here. But I hopefully given you an overview of the ecosystem. There's a few packages even I could not mention at all because they were even more niche. So I thought I would skip that in this call. But you can be very happy if you engage with us and discuss what you might be interested in. So thank you very much.
Okay, thank you very much, Eduardo, for this overview. Maybe we have time for one question, which was quite general. Can we use Scikit-HEP for any kind of machine learning?
Yeah, precisely. So a big changer with this awkward array package is precisely to be able to manipulate the data in a proper way that you can then pipe it into a machine learning workflow. Whether you start with something that is nice and square, as I like to say it, or something that is totally jagged, then you can manipulate whatever that data is and then pipe it to the system. Yeah, that's really one of the big use cases, and that's something we do, right? We do have publications that or analysis ongoing that are doing precisely that.
Okay, great. Well, so it's a very wide ecosystem. Okay, I think we will have to stop here. It's been 2 hours. Thank you very much again for this overview.
Thank you. I'm sorry that this is a bit on the screen. It's really not interactive thing. Interactive store would be a completely different thing, but that's what we can do. And thank you again for the invitation. And I hope you find some of these things at least useful for your work. Thank you.
Sure, thanks. So to everybody, tomorrow is a free day, let's say, because we had a big day for our institute. So we reconvene on Wednesday. Thank you very much, and have a nice evening.